For decades, the consensus in linguistics has been that human speech adapts strictly to social, cultural, and cognitive pressures. The sounds we make are viewed as products of information exchange within our communities. Human vocal folds are sensitive biological instruments that interact constantly with the ambient air we breathe. When we inhale dry air, it strips moisture from the vocal tract. This dehydration decreases the viscoelasticity of the vocal folds, creating friction that requires more physical effort to produce voiced sounds. This raises a specific question. Does this repetitive biological resistance, occurring over thousands of generations, eventually alter the phonetic makeup of a language? If a statistical link exists between local climate and linguistic sounds, the traditional assumption of linguistic autonomy is incorrect. In 2017, Caleb Everett tested this by analyzing over 4,000 language varieties. He hypothesized that languages evolving in drier climates probabilistically utilize fewer vowels. Previous attempts to study acoustic adaptation relied on discrete binning, forcing complex climate zones and language structures into rigid, arbitrary categories. Everett's study tracked the precise, unbroken gradients of global climates using continuous variables. The primary ecological metric was specific humidity, the absolute ratio of water to air in a given environment. By tracking these continuous gradients, the researchers allowed the raw global data to reveal patterns without the interference of human-defined categories. Simply counting vowels in a language's phonemic inventory treats exceptionally rare sounds and highly frequent sounds as mathematically equal. To accurately measure phonetic reliance, Everett used a vowel index. This calculates the ratio of vowels to total sounds across 40 core everyday words, like water or sun. When the vowel index of all 4,012 language varieties is plotted against specific humidity, a global correlation emerges. The positive slope has a p-value of 0. As ambient humidity drops, the reliance on vowels predictably drops with it. While a global correlation exists, raw data alone cannot prove environmental causation without addressing the variable of shared history. This is Galton's problem, the risk of confusing a shared environment with shared genetic or cultural ancestry. If one large language family dominates an arid region, the data may suggest environmental adaptation when the pattern is actually the result of inheritance. To control for this, the study collapsed individual languages into their parent families, treating each of the 229 families as a single data point. Controlling for relatedness did not eliminate the trend. In fact, the correlation became stronger, indicated by the steeper regression line. The correlation survived ancestry controls, suggesting the phenomenon is not an accident of a single language family's success in a specific climate. Neighboring languages often borrow sounds from one another regardless of their ancestry. This geographic proximity is a secondary confounding variable. The researchers isolated these areal effects by running regressions exclusively within major, geographically separated landmasses. The positive correlation between humidity and vowels survives in isolation across Africa, Eurasia, and the Americas. Australia is the outlier, displaying a negative correlation that deviates from the global trend. Australia lacks the extreme cold, dry winters found on other continents. Its reversed trend is driven by unusually low vowel usage in its humid areas, rather than high vowel usage in its dry ones. While Australia follows a unique evolutionary path, most isolated geographic regions independently evolved the same humidity-vowel correlation. To filter out any remaining phylogenetic or areal noise, the study employed Monte Carlo random sampling. The algorithm randomly selects exactly one language per family, ranks them by humidity, and contrasts the extremes. This process was repeated 5,000 times. This density distribution plot maps the slopes generated from those 5,000 iterations. Out of 5,000 iterations, every slope produced across the major landmasses was positive. This result rules out chance, phylogeny, and geography, leaving the environment as the remaining causal signal. Vowels are highly sonorant sounds that require substantial phonation, a process that is physically more difficult in desiccated air. Laryngological data shows that superficial dehydration of the vocal cords requires higher subglottal pressure to achieve voicing. Over centuries, populations may probabilistically favor slightly easier to articulate lexical variants, slowly reducing the reliance on vowels in dry environments. The final data set confirms this pressure. Languages in the driest quartiles consistently lack high vowel indices. The cumulative effect of this subtle avoidance is a verifiable shift in the vowel-to-consonant ratio of a language. This environmental influence is probabilistic, not deterministic. Dry air gently nudges linguistic evolution rather than dictating it. Even so, the data links the acoustic signature of a culture to the physical reality of their geography. Language is a complex adaptive system influenced by social and cognitive variables, but ecology must be included in that list. Modern quantitative modeling allows researchers to reevaluate the assumption of linguistic autonomy using massive, continuous datasets. The data suggests human language is a biological system intimately tethered to the